Hello, Professor. We are Group 7, consisting of Jungwoo Park and Hyunyoung Nam. Today, we will discuss two papers we have selected. The first one is titled Active Learning Helps Pre-trained Models Learn the Intended Task, which was accepted at URIPS in 2022, and we will call this as Paper 1. The second paper, Active Learning by Feature Mixing, was accepted at CVPR in 2022, and we will call this as a Paper 2. Here is our agenda. Let's start with the introduction. Both papers focus on active learning. Paper 1 demonstrates applying active learning to a pre-trained model and results in better performance compared to a non-pre-trained one. Paper 2 introduced a new active learning technique called AlphaMix. But while reading these papers, we noticed a few limitations. Paper 1 did not consider the application of complex acquisition methods or the low data rhythm. Paper 2 did not address task ambiguities arising from spurious features and distribution shift. So we thought, why not blend the insight from both papers? Specifically, Paper 1 just used only uncertainty sampling methods like least confidence. We are curious if applying AlphaMix from Paper 2 would yield similar results. And we also interested in whether AlphaMix would perform well on the dataset used in Paper 1, as it did in Paper 2. So our research hypothesis is as follows. First, we think that utilizing AlphaMix for non-pre-trained models will reduce the performance gap with pre-trained ones. Second, we think that AlphaMix will sustain high performance even with features that contain spurious elements and distribution shift. We are currently conducting this research and we will include the results in our final project, but in today's presentation we will solely focus on explaining each paper. First, let's briefly talk about background of the paper, but due to time constraint we will briefly introduce this, and we have placed the additional background slide in the support slide section. We appreciate your understanding on this. Okay, so active learning is a technique that lets the algorithm choose its data, making it learn better with less training. In passive learning, humans label are all data first, but in active learning, the algorithm selects data to label, which means saving time and effort. So in short, active learning is more efficient. So, objective of active learning is to strategically choose samples that maximizing information gain with some techniques. There are three main scenarios and various techniques, and we will not go into each one in detail. But if I mention what is included in the paper, pool-based learning select the most informative samples from a large pool of unlabeled data. And uncertainty sampling choose samples where the model is least competent, smallest margin, or highest entropy. So the baseline used in paper 1 and 2 are broadly categorized as follows. Okay, so let's move to our main topic. And let's begin with the first paper. Task ambiguity can cause unpredictable model failures. This paper explores if that pre-trained models can be better active learners and perform better than non-pre-trained ones with fewer labeled data points. The diagram illustrates an initially ambiguous task becomes clear through active learning by selecting informative example which is focusing on shape. Okay, this paper has three major novelties. First, paper shows that pre-trained models resolve task ambiguity during fine-tuning more effectively. Second, they achieved the same performance with up to 5 times fewer labeled data points or gain 11% more accuracy with the same labeling budget. Third, paper demonstrate that pre-trained models outperform non-pre-trained models in various active learning tasks. Okay, let's dive into this by one. Let's look at the active learning procedure here. Basically, paper used pool-based active learning. First, the pre-trained model M is initially fine-tuned on a label set S until it converges. And the label set consists of a pair of xi, yi, where xi is the data point and yi is the corresponding label. Next, using an equation function denoted as alpha x semicolon m, the model selects the most informative data points xi from a pool of unlabeled data, which is p. This is done through uncertainty sampling, where the model identifies the most uncertain points. Finally, obtaining labels yi for these selected data points until a budget k is exhausted. The newly labeled batch, which is B, is then added to the existing data S, and the original model M is retrained with these updated data for the next acquisition steps. For the acquisition function, paper used uncertainty sampling, not only risk confidence but also margin and entropy sampling. Moreover, for validation strategy, paper suggests stopping fine-tuning the model once the training loss drops to 0.1% of each initial value. This helps prevent overfitting and means we don't need a separate validation set, which is really useful when data is limited. For the experimental setup, paper used different data sets to test two main aspects. First, paper used a data set to distinguish causal features from spurious ones. They used two vision data sets, which are water birds and tree person. Second, paper measured the robustness in distribution shift using one vision and one text data set, which are iWildChem and Amazon Wilds. These setups helps us evaluate how well the models perform under different challenging conditions. For the vision dataset, paper used BIT models, which are known for their few-shot learning abilities. They used models trained with different dataset sizes and parameters. And for the text dataset, paper used Robots A Large, a model from the BART family, and paper used a random acquisition for baseline, and additionally, to compare with non-pre-trained models, they used a randomly initialized BIT models. Okay, next is experimental results. First one is about distinguishing causal features from spurious one. In the waterbirds dataset, using uncertainty sampling with the pre-trained model boosted overall accuracy by 11% compared to random sampling. It needed 5 times fewer labels and was 25% more accurate on tricky examples with mismatched backgrounds. And in the three-person dataset, paper saw a 2% improvement over random sampling with 1.6 times fewer labels needed. Next is for measuring robustness to distribution shift. In the iWildChem dataset, using uncertainty sampling improved overall accuracy by 9% compared to random sampling and needed 1.8 times fewer labels. In the Amazon Wild datasets, there was an average gain of 1% across reviewers and a 2.5% improvement on the worst 10th percentile, needing 1.3 times fewer labels than random samplings. Also, paper explored different techniques in uncertainty sampling, not just risk confidence but also margin and entropy one. When you see the graph in overall view, uncertainty sampling is better than random sampling, either in distribution and out of distribution. And the paper found that uncertainty sampling tends to acquire more examples with a mix of spurious and core features, which can help the model learn better. Graph for the waterbirds and three-person datasets show that this method focuses on tricky examples with feature complex, improving performance compared to random sampling. And in the Amazon Wild dataset, uncertainty sampling targets lower star ratings and rare product categories, effectively identifying minor groups. Looking at the graphs, we can see that uncertainty sampling, which is the orange bars, selects more low ratings and uncommon categories than random sampling, which is the purple ones. This can enhance model performance by learning from diverse examples. The paper also found that uncertainty sampling improves accuracy only with pre-trained model like BIT, but not with non-pre-trained model like ResNet. Graphs show uncertainty sampling, which is the orange bars, outperforms random sampling, which is the purple ones, for pre-trained models. But you can see that it performs worse for non-pre-trained models. Moreover, paper shows that pre-trained models are better at focusing on disambiguating subgroups by oversampling mismatched background ones. This aids more effective learning. Graph shows that pre-trained models consistently targeting disambiguating examples regardless of background, while non-pre-trained model write down one, oversample images just with water backgrounds and perform worse overall. And if you see from this graph, the graph shows pre-trained models have higher acquisition frequencies for mismatched backgrounds compared to non-pre-trained models, which is red and orange bars. The paper also shows that pre-trained model achieve better linear separability of causal and spurious features compared to non-pre-trained ones. Table indicates pre-trained model, which is the left one, perform better across categories with and without fine-tuning. Paper also includes a TSNE plus of water-birds image embeddings. This shows that pre-trained models create much clearer decision boundaries than non-pre-trained ones, even without fine-tuning. The black stars indicate the acquired examples, and those are aligned better with the decision boundaries for pre-trained ones. And the paper added that with fewer disambiguating examples, uncertainty sampling has a smaller accuracy drop than random sampling. The graph shows that even if mismatches data is decreased, uncertainty sampling maintains higher accuracy compared to random one. And the larger pre-trained model outperformed the smaller one on iWildChem datasets with no difference between models of different parameters counts. So that this suggests that data size is more crucial than the parameter count. Of course, there were also failure cases for the pre-trained model in some datasets. In these datasets, active learning performs comparably or worse than random sampling. So we can say that if a dataset is too irrelevant with the pre-training dataset, like for this case ImageNet, specialized model may be needed. So we've just reviewed the method and the results so far. So the conclusion of this paper is as follows. Pre-trained models with active learning significantly reduce the need for label data and resolve task ambiguity better than random sampling. And we found that non-pre-trained models do not clearly benefit from active learning and often perform worse. Lastly, larger pre-training datasets enhance the active learning's performance more effectively than parameter counts, highlighting the importance of the dataset size.
I will continue with the second paper. Second paper is active learning by feature mixing. Conventional active learning methods either cannot handle or unscalable to the high dimensional data. Also, for cases when there exists limited amount of labeled data, it has to cautiously consider the underlying uncertainty of the model. Intuition of the proposed method AlphaMix is that extracted low-dimensional feature representations can be leveraged to find novel features efficiently, which is also scalable to large dataset without direct application to the high-dimensional input data. Novelties are as following. By interpolating features of representative samples from labeled data and non-labeled data, we can select queried point near the decision boundaries. Finally, for diversely collecting the data without wasting the budget, clustering methods were applied. There were no other active learning approaches with all three aspects. It had shown significant performance training vision transformers and in low data regime. The problem setting is identical to the first paper, pooled active learning. Main difference is that AlphaMix can be scaled up to more large dataset with many classes. To extract representation from the input data, encoder and classifier is trained. Classifier is trained to predict labels with the embedding Z as an input. The network is trained by minimizing the cross-entropy loss over the labeled dataset. For scalable approach, AlphaMix decreases the complexity by using representative points, namely anchor, which is the subset of the labeled data. The mixed feature, which is the convex combination of representations which was calculated from interpolating with the coefficient alpha, can be subjected to the classifier for the label prediction, even for the unlabeled data. It is mathematically proved in the paper The change of the loss can be written as following. When the norm of the alpha stays relatively small, from the equation, there are three terms: alpha, and difference between embeddings of unlabeled and the anchor, and finally the gradient of the loss. In other words, a novel sample is defined based on the largest gradient value with respect to the pseudo label y star. It can be considered as an optimization problem. Objective term encompasses intuition of other prior active learning methods, including gradient-based, adversarial perturbation, and distribution matching. This theoretically supports the remarkable performance of this approach. For alpha, it is empirically shown later that approximated alpha value will harm the performance, but it will have a trade-off on computation time and scalability. Thus, it is recommended for learning the alpha for diversity of sample candidates. Lastly, candidates are filtered when their predicted label changes, and then it is clustered into B clusters, B which is the budget size, and it can be finally sampled from the center of the cluster. This is the final overall algorithm of AlphaMix. For each round, models are trained from the labeled data, and from the labeled data, we initialize the anchors. Then for every unlabeled data, we calculate the embedding Z. And for each anchor points, we approximate with dual norm formulation as following, where I suggested optimize the alpha. Then candidates are selected where predicted labels of unlabeled embedding and interpolated embedding differs. Finally, we cluster the selected candidates to B clusters, sampling from the center of each clusters, and the process repeats. This study had applied AlphaMix to 12 datasets with various settings, including model architecture, initialization method, budget size, and active learning method. The results are all clearly stated. Figure shows that the percentage of rounds when AlphaMix performed better than other baseline. We can see that AlphaMix consistently outperforms others, especially with the vision transformer and the low data regime. Other competitive methods are batch and CDAL. They also have relatively high performance compared to each other baseline. The last row shows the average time each method is outperformed, and we can see that for CDAL and batch, it is relatively comparable to the AlphaMix. We can see that from the figure, the CDAL and batch are outperformed by the AlphaMix about every 1/3 rounds, but not in the opposite cases. We can see from the figure that AlphaMix selects sample near decision boundaries, which is more diversely scattered compared to other methods. This shows that for different kind of model, including vision transformer and MLP, AlphaMix consistently shows high performance. On the low data regime, in the video classification task of HMDB dataset, it also showed the significant performance, improving each round compared with the random method. These are the ablation study results of candidate selection method, learning alpha, and using anchors. The results suggest that k-means clustering and optimizing the alpha and using anchor was the optimal result. These results suggest that it has efficient computational time, significantly faster than other competitive method batch. This is also comparable to the simple method of entropy. In conclusion, the effectiveness of the alpha mix was evaluated in various settings which achieved significant performances. It is applicable to low data regime compared to other baselines, suggesting that the future interpolation method can reveal meaningful variations in feature representations. Thank you for listening.